39th lecture on digital circuits. We shall not be able to do much of digital circuits, so we will learn a bit of Boolean algebra in the last two lectures, 39th and 40th, but the basics only. All we have seen is that a diode as well as a transistor can act as a switch, and a diode circuit is, if you have a diode like this with, let us say, a resistance and a battery, let us say 5 volt battery and some resistance R sub C, then we have shown in the previous class that if this is high, if this is high, higher than 5 volt, then this will also be high, whereas if this is low, that is less than 5 volt, then this diode shall conduct, and if this diode is ideal, there shall be 0 volt drop, and that shall also be low. The high level is characterized by a digital or Boolean 1, and low level is given the status of Boolean 0, logic 0, 1 and 0. There are philosophical interpretations of this. In fact, the Boolean logic arose in philosophy to start with, Western philosophy. 1 is for true, 0 is for not true or false. But in our context, since a circuit is either on or off, that is, the voltage level at each point in a digital circuit is either high or low. If it is high, it's termed status 1. If it is low, it's termed status 0. The low level can have a range of, let's say, 0 to 0.6. The high level can also have a range, maybe between 4 and 5.5. all right, and therefore the exact level is not important. What is important is whether it is high or low. In a similar manner, if we take a transistor circuit, a transistor then you know that if VBE, if this voltage is high, then this voltage shall be low. If this is high, then the transistor will conduct heavily, the collector current would be large, and therefore this voltage would be VCC minus the drop in the collector resistance, and therefore this voltage shall be low. And if we overdrive the transistor, then we shall be operating in this region of transistor characteristics, which is the saturation region, and this voltage is usually taken as 0.2 for silicon, and therefore the low level for a transistor switch is approximately 0.2 volts. On the other hand, if this voltage is lower than 0.7, the threshold, then the transistor does not conduct, and therefore this voltage shall be high. If the transistor does not conduct, then the total VCC shall appear at this output point, and therefore the voltage shall be high. You notice that there is an inversion in the transistor circuit. That means if the input is high, output is low. If the input is low, the output is high. And in general, if the input is denoted by the Boolean variable capital A, then the output is the complement of A. That is, if this is high, then this is low. If this is low, then this is high. Capital A can take on, a Boolean variable can take on two values, either 0 or 1. This is the basis of digital circuits, and all that you see in the modern world, whichever walk of life you are in, computers are a must, and computers operate with these two basic components. There are modifications to make the switching speed, that is from low to high, switching speed large or small. Interconnection lengths also decide whether switching shall occur properly or not. Those are matters of detail, and the digital circuits are made in the form of chips, very small. They occupy very small space, and therefore they are very popular. And the other reason is the accuracy, that is, the actual voltage level is not important. What is important is whether it is low or it is high. Naturally, the arithmetic that is to be used for analysis and synthesis of such circuits, because there are only two levels, 0 and 1, the most eminent kind of mathematics is the binary arithmetic. The binary arithmetic, in which there are only two digits, namely 0 and 1. Therefore, decimal 0 is 0, decimal 1 is 1, decimal 2 is 1 0, decimal 3 is 1 1, decimal 4 shall be 1 0 0, and so on. Okay? And you know how to convert a given binary number into a decimal number. All right? A given binary number, for example 1 0 1 1, what you will do is multiply 1 by 2 to the 0, 1 by 2 to the 1, 0 by 2 to the 2, and 1 by 2 to the 3, and add all of them. That is the binary. Given a decimal number, let us say 235, to convert it into binary, you know what you do. You go on dividing by 2 and note down the remainders. Then you arrange the remainders in the reverse fashion. On the other hand, if this is a fraction, let us say 0.235, you go on multiplying by 2 and collect the carries, not remainders. Collect the carries. For example, the first multiplication will give a carry of 0. Second multiplication also shall give a carry of 0. Third one, 1. And therefore, this will be 0.001 and so on. For converting a decimal fraction to a binary fraction, the carries are arranged as they appear. On the other hand, if it is an integer number, then the remainders are arranged in the reverse order. Okay, these are known to you. Most of the discussion that we are going to do today, in fact, are known to you. And if we arrange two diodes like this, and this is connected to plus 5 volt through a resistance R, all right, then obviously there is a ground. There is a ground because voltages have to have two terminals. Voltage is a potential difference, it has to have two terminals. This 5 volt battery has a ground. Then you see that if the state of this input is called A and if the state of this input is called B, then the state of the output, which we shall call C, shall be determined by the states of A and B. And you see that C shall be high when both A and B are high. And this is represented by the so-called truth table, as you already know, represented by the so-called truth table, and the possibilities are A and B both can be 0, this can be 0 1, this can be 1 0, or this can be 1 1. These are the only 4 possibilities, all right. And C is high only when both are 1, so all the rest must be 0. And this, in terms of Boolean algebra, is represented by C equal to A and B. This is called an AND operation, and this is an AND circuit. This is an AND operation, and the circuit that you see is an AND, and this is usually represented by A dot B. Dot stands for the AND operation, but for brevity, when you have to write it again and again, we usually omit the dot, all right. Even if it is omitted when A and B are written adjacent to each other, it means that A is ANDed with B, all right. This is the AND operation. This is one of the basic logical operations. The second basic logical operation is OR, and the circuit is very similar except that the diodes are reversed. The diodes are reversed and there is no battery needed, there is simply a resistance needed. This is C, this is A, and this is B. And you can see that C shall be high when either A or B is high. When A is high, the diode is a short circuit, this diode is a short circuit irrespective of what this diode is, and the high voltage appears across C. Or when B is a high, then this diode conducts, it is a short circuit, so the high voltage appears at C. When both of them are high, then also it is high, but if both of them are low, then obviously C shall be at 0 potential, that shall be low, and therefore the truth table is, once again the possibility of the variables are 0 1 1 0 1 1, and the output shall be 1 when either or both are 1, and therefore this is the only situation in which it is 0, all others are 1. And in terms of Boolean algebra, this operation is represented by the plus sign. Now we cannot omit the plus sign. Okay, this plus stands for logical OR operation. So it is A or B, A or B, and this is a simple diode logic. Usually one does not use diodes to realize such gates, one uses transistors, and in various kinds of families, the most popular family at the present time is the MOS family, metal oxide semiconductor, which we have not discussed in the class. Metal oxide semiconductor because they occupy the least amount of space. But as far as speed is concerned, now speed is important here. For example, if A is high, all right, then C is high. Suppose from high A is reduced to 0, how quickly C can follow this operation? Obviously it cannot. Why? How quickly C can follow? Because if A is high, then the diode conducts, which means that the, what does diode conduction mean? It means that the space charge barrier, the charges come close together, all right. So the diode conducts. Now as soon as the voltage is withdrawn, the charges cannot recede instantaneously, they take some time, all right, and this time is the so called, determines the so called speed of operation or the speed of this circuit. And in high speed digital computers as they are at the present time, diode logic is out of fashion. Diode logic cannot be used. We are using it simply to illustrate the basic circuit, to understand the phenomenon of the OR operation. And the third basic gate, one is, first is AND, second is OR, and the third basic gate is the NOT gate or the inverter, which is simply a transistor in which, in order to make sure that a low voltage, that there is no ambiguity in the low or high operation, what we do is, besides R sub C, what we do is we use a resistance here and bias the base negatively, all right, maybe 1 volt is good enough, all right, so that only when, well, usually this is also set at the same value as plus VCC, all right, we will call this a VB, some voltage VB. Then you see this voltage has to overcome the negative voltage in order that the diode conducts, all right. And as I have already told you, if this is A, then this is A bar, and this is called a NOT gate or an inverter. One can make a combination of these three basic gates, that is AND, OR and NOT, to be able to derive more complicated gates. You understand why they are called gates, because they either allow a high level to pass or they don't allow, so they are called gates, logic gates or digital gates, all right. One can make combination of this. For example, if an OR is followed by a NOT, well, the operation is NOR, all right. Have I? Yes. Pardon me? Yeah. Okay. So this kind of a circuit drawing will not be valid in the case of digital circuits. We'll have to give symbols. This is why I drew it, to be able to create a confusion. This will not hold in the case of digital circuit. We must draw a symbol. We must indicate the number of inputs. For a NOT gate, there is only one input and there is one output, and therefore this type of circuit shall not be valid. Our representation, the universal representation or IEEE representation is, for an AND gate, this is the representation. This is AND. To make it specific that this is AND, sometimes a dot is put here, sometimes it is not needed. For an OR gate, the input line is curved and the two side lines are also curved, and there are two inputs. This is called an OR gate. So if this is A and this is B, then the output is the ANDed form of A and B, whereas in the OR operation, to make it specific that it is OR, sometimes a plus sign is put, but whenever you see this peculiar shape, well, you know it is an OR, and if this is A, this is B, then the output is A or B. For a NOT gate, one input and one output, and this is usually represented by a triangle. A triangle is used for an amplifier in analog circuits. In digital circuits, it represents an inverter. Triangle with a dot. This dot represents complementing or inversion. All right. A NOR gate shall be represented by an OR to start with. It takes two inputs, A, B, and then an inverter. So this is A or B, and this is A or B complement. This is a NOR gate, and naturally for a NOR gate, the truth table shall be A, B, and then A or B complement. It would be simply the complement of the truth table of the OR gate. For example, 0, 0 shall give you 1, 0, 1 shall give you 0, 1, 0 shall give you 0, and 1, 1 shall give you 0. This is the NOR gate. All right. I must mention here that in modern integrated circuits, one does not make, the manufacturers do not make all the three kinds of gates. They make only, a particular company makes usually only one kind of gate. It's either NOR or NAND, N-A-N-D. And NAND is AND followed by a NOT gate. And the argument is, the logic is that the production of 3 different or 4 different kinds of gates is much more costlier than producing the same gate maybe 4 times or 5 times the number, because each process step in integrated circuit technology, each process step variation costs you a lot of money. All right, and therefore fabrication companies prefer either to manufacture NOR or NAND. However, there are companies which manufacture both NOR as well as NAND gates. Okay, a NAND gate, as I said, is an AND with 2 inputs A and B followed by a NOT. This is AB and this is AB bar. This is a NAND gate, and the truth table can be written as the complement of the AND, that is 0, 0 shall be 1, 0, 1 shall be 1, 1, 0 obviously shall be 1, and 1, 1 shall be 0. Okay. If you compare the NOR and the NAND, don't you see a similarity? Yes or no? 0, 0 is the same. No, there is no similarity. There is no complementarity either. NOR and NAND, but nevertheless one can realize a NOR function if you have only NAND gates. In fact, In fact, it can be shown, and you try this out. This must be several tutorial problems in the textbook, that given a NAND, given any number of NAND gates, you can realize any other gate, including a NOR gate. For example, if you want to convert a NAND into, let's say, an inverter, a NOT gate, all that you do is you connect the two inputs together, all right. Then this is A and this is A bar. Is there any other way that I can make it? Is there any other way? I have a NAND gate. I want to make an inverter.
Using only one.
Yes, using only one NAND gate. This is my input A. What should I do with the other? One of the ways is I connect it to A. Pardon me? You have a 1 here, then A and 1 is A, and pardon me? A and 1 is A. All right, that's it, and therefore the output shall be A bar. This is another way. All right, there are alternatives also, but anyway, the point that that is interesting is that only one type of gate suffices to realize any other function. And before I go further, let's see the NOR gate. The circuit shall be first an OR minus VB and then a NOT. Is this a NOR or A or B? If either is high, then this will be high, therefore this will be low. Yeah, this is the output shall be A or B complemented. Given a circuit, you must be able to detect what kind of a gate is this. This is a NOR gate. All right. On the other hand, if I want to make a NAND, all that I shall have to do is to reverse the two diode polarities. All right. Let's see this. A, B. Then, do I need a negative bias here? No, I need. Let me draw this circuit, then I will tell you why it is so. RB, then this require a little bit of experience to appreciate why it is so. And this is connected through a diode. The base is connected. This is a practical circuit for a NAND gate. Now, why are all these paraphernalia needed? Why a diode and an RB needed? You see, when both, as I said, this is a NAND gate, when both A and B are high, then the two diodes do not conduct, all right, and therefore VCC through RB and this diode drives the transistor, and the output shall be high or low? Low. The output shall be low. When A and B are both low, when they are both low, what happens is, both low or one low, it doesn't matter, right? One of them low, then this becomes approximately connected to ground. If this is an ideal diode, then it is 0 voltage drop. If it is non-ideal, as is the case in practice, if it is a practical diode, then there shall be a drop of 0.7 volt. Now, if this diode was not there, then this transistor would have conducted, because 0.7 is the voltage required here. This is why another diode is inserted, so that when this voltage is 0.7, this combination requires 1.4 volt to be able to conduct. Isn't that right? 0.7 here and 0.7 here. So, it makes sure this diode, you must understand the function of this diode. This diode makes sure that when one or both of these diodes conduct, that is when A is low or B is low or both are low, the transistor does not conduct and the output is indeed high. The transistor does not conduct and therefore the output shall be high. Is the point clear? Why a diode is needed here? It was not needed in the NOT circuit. All right, it was not needed in the NOT circuit. So this is a NAND circuit.
So if the diode had not been there,
Yes.
then would it have conducted or?
Yes, if the diode was not there and this is low, then this would have conducted, this diode, and because it is a practical diode, the drop across it would have been approximately 0.7. And if this drop is 0.7 from here to ground, obviously the transistor would have conducted. We want to make sure that it does not conduct, so we put another diode. It will require 1.4 volt, and for this diode to conduct we require 0.7, and therefore this indeed, the diode indeed is needed. As an illustration of how a NAND gate can be used to realize any operation, can you make an AND out of NAND? Yes, all that you require is another 2 NAND gates shall be required. One is NAND them and then another inversion. For an OR circuit, for example, where what you require is, now from now on we shall represent the output of a logic circuit, digital circuit, as small f, all right, function. If I want the OR operation, what I want is that f should be equal to A or B. I want to convert this into NAND type of operation. So what I do is, which we shall do a little later, we use De Morgan's theorem. What we do is A, not B, then complement. All right? That's what we shall implement now. One NOT gate, one NAND shall be required for A bar, one for B bar, and the third for NAND, that is A bar, B bar, NAND. If I can draw them, I can draw them very easily. What I have is, this is A, so this is A bar. Similarly, this is B, so this is B bar, and then I put them together to a third NAND, so I shall get A bar, B bar, whole bar, which is equal to A or B. Similarly, try it out how to make other functions. Well, what is the other function left? NAND, well, AND, OR, and NOT. All the three can be realized by NAND gate. Similarly, try with NOR. Try with NOR. From NOT to OR is very simple. From NOT to AND is not difficult either. From NOR to NOT, NOR to NOT. How do you do that? Same as NAND. That means you connect the two together. There is still another way. One of them is to be connected to 0. All right. Then some terms as are used. The computer science boys should be very familiar with this. A bit, terminology is used in digital circuits. A bit is an abbreviation of binary digit. All right, this B and IT, binary digit. 1 or 0 is a bit. A word of 4 bits is called a nibble, okay, and a word of 8 bits is called a byte. All right, a word means a number, a binary number consisting of 8 bits. If well, you understand what we mean by word. By word we mean the number of well, it's a binary number. It's a binary number, and the number of bits making it is called the word length. What is the word length permitted by the ICL system here? How many bits are permitted? 32 bits. Yeah. Okay. Some standard terminology. Then some postulates of Boolean algebra. Postulates and theorems. The basic postulates are, of course, the three operations. That means OR, AND, and NOT. Okay. OR operation is 0 or 0 is 0. These are the postulates. This is what it starts from. And you see, this can be converted into a digital circuit, either with diodes or with transistors or combinations. 0 or 1 is 1, 1 or 0 is 0, and 1 or 1 is 0. Okay, thank you. And in AND, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 0. Okay. All right. In the NOT operation, complement of 1 is 0 and the complement of 0 is 1. They look very simple, but in complicated Boolean expressions, sometimes one has to refer to this. Sometimes one has to recall the roots. But it's obvious that if I complement A and complement again, this should be the original A. All right. This is the relationship in one variable. And if I generalize this, these postulates, these are specific values that we have taken, 0 and 1. Suppose I take a Boolean variable A, which can be either 0 or 1, then its operation with the two bits that are available, that is, if we OR A with 0, we shall get A. Okay. A with 1, we shall get, sure, not A? Okay, 1. If we OR A with A, we get A. And if we OR A with complement of A, it is still 1. All right. On the other hand, if we AND A and 0, it would be 0. A and 1 is A. A and A, and A and A bar. Good. And NOT operation, of course, there is only one, that is double complement of A is A. All right. Let's take two variables now. Two variables or two or more variables. Okay. Two or more variables. If we wish to write such rules or such consequences, it will take a long list. So we group them into rules or laws, as they are called. One is the commutation rule, which says that the order of operation is not important. That is, whether you OR A with B or B with A, it is not important. All right. They are identical. This is called commutation rule. You can bring B first and then OR with A. 1 plus 1 or 0 and 0 or 1 are the same. Okay. And the other is, if you AND A with B, the result is the same as B ANDed with A. This is commutation rule. This is true in ordinary arithmetic also, decimal arithmetic also. Okay. Commutation. Then the second rule is association. In association rule, A or B or C, there are more than two variables, A or B or C. That is, this operation says that B should be ORed with C first, then ORed with A. Well, this happens to be the same as if A is ORed with B and then the total is ORed with C. Or you can make any other combination. For example, it could be B ORed with A instead of A ORed with B. Okay. Similarly, in the case of AND operation, that is A and B and C, which indicates that B and C have to be ANDed first and then the result is to be ANDed with A. Well, you can write as A and B and C. All right. This is the rule of association. Well, so far these are all trivial and revisions. De Morgan's, the third set of rules is given by the De Morgan's theorem, and it states that if you have an OR operation followed by a complementation, then this is complementation of the two variables and an AND operation. The two are equal. This is one form of De Morgan's theorem. You must follow this. OR operation is converted to an AND. OR is converted to an AND, and the result is that both the variables have to be complemented first. And the easiest proof of this is by writing the truth table. All right, easiest proof. In fact, if you can't make a mistake in proof if you go by the truth table. But sometimes truth tables are very long to write, and things may be obvious. We'll show examples of this. The other is that if A is ANDed with B and the whole thing complemented, this is one form of De Morgan's theorem. The second is A and B, the result is complemented, then this is simply OR operation between complement of A and complement of B. Once again, a AND operation is being converted to OR, but complementing is a part of De Morgan's theorem, is an inherent part of De Morgan's theorem. Whenever you want to convert one operation to the other, OR operation to AND or AND operation to OR, you must complement. Okay? And De Morgan's theorem without complementation is not valid. Okay? One is to remember this. Then the fourth set of rules are the absorption rules, and these are interesting. That is, A or A and B, A or A and B is simply equal to A, and the proof here is very simple. A can be written as A and 1, and this can be written as A and B, and by how can I do this? A and 1 or B? Association, distribution, which you have not proved yet. Okay, but anyway, 1 or B, 1, and therefore this is A. And the second distribution law, second absorption rule, this is 1. The second follows from this. Here is an OR operation, so you replace this by AND, this OR by AND, and this AND by OR. A and A or B is equal to A. Why is it so? A and A is A and B, and A plus AB is A. It takes account of the first rule. And without distribution, the easiest way to prove is to write the truth table. If you don't want to take distribution, okay, if you are barred from using distribution, then this is what you do. You write the truth table. And then the distribution, finally. You could do distribution earlier. Distribution rules are again 2 in number. That is, if you have A and B or C, you can write this as A and B or A and C, exactly like ordinary decimal arithmetic. However, there is a difference. If this is replaced by OR, this is first form. The second form is this is replaced by OR, and this is replaced by AND. Then this is equal to A or B and A or C. And the proof of this, easier proof, is to go from here to the left. If you expand this, you get AA, AC, BA, BC. AA is A, absorption. A plus AC is A. A plus BA is, and therefore this is A plus B. Is that okay? All right. You can have fun. There are several problems in the tutorial sheet which asks you to prove that the right hand side is equal to the left hand side. The important thing is, well, you shall be able to do it blindly if you proceed by truth table. But suppose there are 3 variables, 3 inputs, then how many lines will be there in the truth table? 8, 4, 16. If it is more than 4, then you have had it. Your one page may not be able to accommodate it. It is better to look for simplification. And it is important to see which side should you start with. And this will come through experience. That is, if you work out more and more problems. Now, as in analog circuits, we can have 2 kinds of problems. We can have analysis or we can have synthesis. All right. Logic circuit analysis means, given a logic circuit, find out the output variable in terms of the input variables. Exactly that is what we do in analog circuits. Given an analog circuit, find the output in terms of the input or inputs. You can have more than one input. All right. For example, in a transistor amplifier, what do you find out? The output consists of 2 parts, the AC and the DC. There are 2 inputs. One is the DC. Where is the DC? VCC and the signal. All right. There are 2 inputs. Okay. So logic circuit analysis means that you want to find the output in terms of the input or inputs. All right. Another objective of logic circuit analysis is simplification. It just doesn't stop at finding f as a function of, let's say, the inputs A, B, C, etc., etc. It doesn't stop there. It's logic circuit analysis in this term is implied whether you can simplify the expression, that is plus simplification. That is, one might have what do you call an immature person? Amateur. An amateur might have constructed a circuit which can be done with less number of gates, and therefore one should look at whether you can simplify this or not. And one of the we shall illustrate this by means of a specific problem. But you understand the difference between analog circuit analysis and digital circuit analysis, logic circuit analysis. Logic circuit analysis, in addition to finding the output variable, it also implies whether the same output variable could be obtained from the same inputs by a simpler circuit. All right. An example. Suppose we have 2 variables A, B, and we have a series of NAND gates. One, now let me tell you what I mean by this. And B. This means, this dot here means that a inversion has occurred to start it. For example, if I have, let's say, A, and then I apply to an AND gate, I represent this sometimes. It's convenient to represent it not by drawing another gate, but by simply doing this, which means that the actual input to this gate is complement of A, not A. All right. Not A, N-O-T, N capital O capital T capital, not the English not. All right. Okay. So this is another gate. This is an AND gate, and the third is, now you see I am not bothering to draw these tweedles. Whenever there is a connection, I will show it by means of a big dot like this. If there is a crossing like this, that means they are not connected to each other, because otherwise I will have to draw so many tweedles. I don't want to do that. all right, and the third gate is a similar one, but the inversion operation is in B. Okay, all these three are brought to an OR gate, and this is what is F. One can one can very simply see that this is AB complement. There is an AND gate. This output is A bar B. There is an AND gate with A complemented, and this gate is A B bar, and therefore F should be simply equal to the OR between these two, that is A B bar plus A bar B plus A B bar. Now this is, as far as analysis is concerned, you have obtained an expression. Can it be simplified? Well, try this. By De Morgan's theorem, this is A bar plus B bar, then A bar B plus A B bar. Now you combine these two, this is A bar, and these two will give you B bar, which you can write as, all right, and therefore all this is redundant. What you could do simply with one NAND gate, isn't that right? This is A B bar, and therefore all this is redundant. This is the work of an amateur, and you must look at it, all right. It is very important for a company that they have expert logic circuit designers, because if one is not an expert logic circuit designer, the company might go bankrupt. All right, we shall have a few minutes break before we take the 40th lecture. We shall assemble here again at 5:03. All right.